Now we move to the next topic in spherical mirror, and it is finding relation between focal length and radius of curvature. We have already learned the derivation part of it in lower classes, where we have derived the relation between focal length and radius of curvature, and it is f, which is representing focal length, and r representing the radius of curvature. So this relation is f is equal to r by 2, that is focal length is half of radius of curvature. Now this we have done in lower classes, and we have done it under the assumption that rays are paraxial. Now when we say paraxial rays, we mean rays close to the principal axis. Now for sake of better understanding and to penetrate more into it, here we will take up the general derivation. Let's consider a ray parallel to principal axis hitting the mirror at point A. The relevant figures are shown on the screen. The point of incidence is A. Now we draw normal, and it will be through center of curvature. Let our ray makes an angle theta with the normal. So from the laws of reflection, this ray will get reflected off from the mirror, making equal angle and cutting the principal axis at point F, which by definition will be the focus. Pole of the mirror is shown, principal axis is shown. The same situation is shown for a convex mirror also. Here the ray parallel to principal axis will appear to come from focus. Now we need to calculate FP, that is by definition the distance between focus and pole is referred as focal length. Now in triangle CAF, we draw perpendicular from the focus on the other side, cutting the opposite side of the triangle at point M. Also from routine and regular geometry, the relevant angles are shown, and we find that this triangle CAF is an isosceles triangle. Base angles are equal. Now angle ACF is equal to SAC by very property of being alternate angles. Similarly, the angle CAF is equal to CAS, again by using the second law of reflection, which says that angle of incidence is equal to angle of reflection. Now considering the right angle triangle CMF, we find the value of CF, that is the distance of focus from center of curvature, and it works out to be r by 2 sec theta. Now here we are making use of the fact that this perpendicular drawn from F on the opposite side of triangle CAF will bisect it. Because base angles are equal, it is an isosceles triangle, and we know from the lower classes that perpendicular drawn from opposite vertex will bisect the opposite side. Hence CM will be r by 2, CA will be radius of curvature, so we can represent it by r, and CM will be r by 2. Hence we get the value of CF r by 2 sec theta. Now to find out FP, which we can simply see from the figure that FP will be CP minus CF. Now again CP will be equal to radius of curvature. Hence we get a general relationship F is equal to R minus R by 2 sec theta, where theta is the angle of incidence of a ray parallel to principal axis. Student, please take care of this relationship, and this relation, general relation, will explain many more points. Now we consider the case we have studied in lower classes for a paraxial rays. Now we will be dealing with mainly paraxial rays. Sometimes in some of the numerical problems we will be referring to marginal rays. Now the definition of paraxial rays is very simple. The rays which are close to principal axis are referred as paraxial rays, and the rays which are far away from principal axis are referred as marginal rays. Now considering the situation that our ray is paraxial, so we can have approximation, and it is clear from the figure that the angle of incidence for paraxial rays will approach to 0. Applying this consideration in the general equation we have derived just now, we get F is approximately equal to R by 2.